Dad!
I knew I should have locked that door. Welcome back. The first thing I want to do is apologize, okay? Mom always said, don't ever apologize right out of the gate because it's going to put people off. But I have to apologize. I'm sorry it's taken so long for us to drop our next episode. But I got to tell you, it came out of 26 man-hours of work, and all of which is captured in raw video, and it has to be edited. So this is going to turn into a series. We're going to break this down into parts for you, okay? We're going to cover the mechanical stuff. We're going to cover the electronics. We're going to cover recapping. We're going to explain how the tubes work and what they're expected of them. So in order to accomplish that, we've got to break this up into a series. All right. I want to be able to show you different aspects of things to look for. Okay. Things that I'm looking for. And for you DIYers, I'm hoping that it's going to basically bring to the fore techniques that you'll be able to use if you're going to be working on your own stuff. Okay. And in order to accomplish that, let's go back to the lab.
So, I found something that you might be interested in.
Oh, great. What, another lost puppy?
Yep. Here's good. Sit this all aside real quick.
Sure, no problem. Just what I've always wanted, a cardboard box.
Yep, and I have two of them.
What do we got? Holy sh...
Yes, so... Quick 101 on Griffin.
Yeah?
This is before the name Denon came to America.
That's why it looks like a Denon.
And,
so this is hopelessly tubes.
You're getting ahead of the game, but you're correct.
Porn!
Well, you're gonna be disappointed actually. This doesn't have a schematic.
Oh, well. No, why make it easy?
Right.
4-track stereophonic 1962.
You got a piece of wood by chance somewhere?
Oh, it's a rather personal question.
Well, I don't want to care about that one. There, that right there, yeah. And just leave it there so I can get you the next thing.
Some assembly required. Wow, this is in super condition, man.
I was really happy to find this one.
So which one is this? Because there's two different types of models. There's a 707A and a 707B, which is a 3-speed.
Yeah. This one is a 707A, 4-track, 2-channel, 2-speed machine.
So 2 speeds being probably 7.5 and 3 3/4.
So there's a sleeve on the capstan that you actually have to twist off and then pop that off, and then there you get your 3 3/4.
Okay, is there a place to store that so it doesn't get lost?
I didn't find one.
Uh-oh.
So you're kind of on your own on that one. This doesn't even have lifters whenever you fast forward and rewind.
Yeah.
Pull the tape down.
Right.
You actually have to manually bring down the cover in order for you to actually take the tape off the heads when you shuttle fast forward and rewind. So that's how primitive this is.
But I can't get over the condition this thing is in. Because, I mean, this thing is, well, 62, so 62 and 40 to 2002 is 40 plus 23. Is 63, 62 years old?
Yes.
Did I do the math right?
So from 1962, and it's 62 years old.
Okay. And 2 times 2 is 4.
4.
And it's 2024. Okay.
Yeah.
Okay, so we have synchronous motors here.
You have 3, and it's solenoid-driven. The power comes from the RP unit, so there's actually a Cinch-Jones connector back there that runs the RP power and functions.
Right back there.
And so...
Hang on. Are you sure this is a match set?
It came this way.
Are there instructions?
I mean...
Tab A into slot B.
Is it really that easy?
No.
But check this out.
Yeah?
So you see this transport.
Yeah.
I can already tell you that that's a different picture of an RP unit.
Yeah, because the switches are on in different places.
Switches are in different places.
So this is a 725. What model RP unit is this?
I don't know.
All right, well, these are at least labeled to Mecha, which means we have to point this that way. So this one's going to fit there. And this one is going to fit there. So this is the record head. But
Oh, geez.
that's a 6-pin Cinch Jones connector, and it's a 4-pin on this unit.
Okay, I'll admit that I did not see that at first.
It's not a deal breaker.
Yeah,
It is not a deal breaker.
Well, can you still get Cinch Jones connectors or something?
Oh yeah, absolutely. I don't want to set this on the knobs or on the meter faces, so I'm just going to set this down here. I mean, what's the backstory on this?
So there's actually a thread on the internet about this very machine on Tapeheads, the website
Okay.
Tapeheads,
Okay.
about the Griffin 707A. And the gentleman that actually owned that machine that made the thread decided to sell it. And so I reached out and asked him if he was willing to sell it because there's not a lot of information on this machine at all. The only thing I can tell you is that the name Griffin came because they were trying to appeal to the American market. And instead of going with a name like Denon, just like Akai and Roberts.
I was
did.
going to say.
Yeah. So here's something you need to notice. I'm going to grab this camera right here. This
I could if you held the camera still.
Well, thanks. I say the same thing about you. But this is a 100-volt AC motor.
Okay.
And that's what gives me the assumption that this is actually a
Japanese machine.
foreign unit, yeah.
Because it's operating on 100 volts.
That's what the motors are asking for. But yes.
Okay, but that's a supply motor. Does the take-up motor have the same markings on it?
As a matter of fact, it does.
Really?
Yeah.
It's got 3 motors. What's a capstan motor say? I'm not sold.
All right. Well, I'm going to put this on its side.
Wait a minute. Stay there. Look.
Yeah.
Okay. Right there. 1,800 RPMs, 60 cycles, so we know it's America.
Okay.
117 volts.
So why is it that the take-up and supply motors are 1 voltage and the capsule
Because
is another?
typically they're not going to really have to run at full voltage. The only time they're going to get full voltage is when they're fast forwarding or rewinding, when they're in shuttle mode. Now, as far as torque is concerned, all 3 of these motors are going to have hysteresis capacitors on them for torque reasons. But we want to make sure we get the voltage right. In fact, I'm looking right up here. I'm looking at this resistor, and that's a heavy duty. It's a 5-watt wire wound. Okay. That may very well be the dropping resistor for those motors.
I'm going to set this aside, but we'll take a look at the RP unit and see what that looks like.
It looks like an RP unit.
I'm glad you think so.
The first thing we do is we take a Post-it so they don't get lost. And that's crinkle paint. Wow.
I'll take that for you.
Okay. Needs to be cleaned up a little bit, but 60 years old?
62 years old.
Because that makes all the difference. We've got AX7, 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 AU7. AU7 is going to be a medium amplification factor, whereas the AX7s are going to be a high amplification factor, what they call high mu,
Okay.
MU. Okay, so the AX7s are going to be providing a tremendous amount of gain, and then the AU7 is probably just going to be sort of a buffer stage going into the finals. So we've got another 12 AU7 down here, and with this can here, I'll bet you that's a transformer. This has got to be the bias oscillator.
Okay. For recording?
Yeah.
Okay. Is that a 6x6?
6X4, I think.
6X4.
6X4, yeah. Full wave rectifier. And then these cans here, of course, are all those filter capacitors, and these are all duals. Okay, there's 40 and 40, 20 and 20, 20 and 20, 20 and 20. I think I've seen everything I need to see on this side.
So, do you feel like you want to use the Variac, or?
Absolutely.
Okay.
I would not, I'm not going to diddle with this without having some kind of protection.
Because they're tubes, right?
Because they're tubes, mostly because it's old.
So we're going to put this right here. I guess do the only 2 out of 3 Cinch Joneses that we can do.
This is the record head and the erase head, I'm sure.
Yeah. Yeah, I don't think you want to put the erase head on the 4 pins it takes to run the playback heads.
No, because it's probably got close to 80 volts coming out of that. So what do we want to do? You want to basically put some juice to it?
Put some juice to it on the variac
And look for smoke?
And look for smoke, yeah. So
before we can actually fire this thing up and leave it running long enough to actually do some checking of the RP unit and so forth, I want to go ahead and just oil up the motors. The filler tubes on this motor are facing up, so I'm going to go ahead and do this one while it's here, but I'm going to need it closer.
okay. Yeah, because I see the filler tubes are on the very bottom of the capstan.
I'm not going to actually dribble that into the tube. I want to use my eyedropper.
Oh, okay. I never thought to use an eyedropper.
Now we're not going to lubricate these with the motors running. We will spin them manually at first, just to get the oil around inside there. I know it was probably lubricated at the factory. I'm going to assume that those motor shafts are dry. What I'm going to do is I'm going to just insert this into this tube here. I'm going to blow some bubbles, and then I'm going to draw the oil into the eyedropper. And I'll probably put half of this in the front and the other half in back. Okay, it just fits right in there. So I'm just going to gently squeeze the bulb, and it stops. That means the tube is probably full. Now, I don't know if we can get to the solenoid on that. Let me see. I think this is it here.
That's it.
Okay. Just give it some really good spins, maybe for about 10 or 15 seconds. Have you noticed any difference?
Not immediately, but I mean, I feel better about spinning it.
And this is just going to soak into that, kind of like a sponge. It's just felt. I'm going to do the other side now. Gravity is actually going to feed this, and that's plenty. I don't know about you, but that looks like it's better. Okay, I think that's got it.
Do you notice the name Denon on the motor heads?
Yes, it's like, okay, secret is revealed. This has actually got a date stamped on there, 1962. But it was probably released in 1963, but I mean, the parts are manufactured in 62.
That's really what matters, though.
Again, I just want to be able to fire this up and leave it running so that I can be working on the RP unit and actually determine what, if anything, needs to be addressed in the RP unit. Clearly, there's no load on there right now, so I'm just going to back this all back down.
Okay.
Give me the power.
Oh, I'm feeling vibrations. Well, I'm just...
Gotta keep those loving good.
You sing so good, we're going to get copyright struck. Probably the capstan motor.
So, yeah, it wants to run. I'm not seeing anything else going wrong.
Okay. Yeah.
Not yet, but I'm only at like 25 volts.
Yeah, you can see.
There's 30.
All right, the fan is slowly spinning on the capstan, so this is probably like an always-on motor.
Okay, but I'm not seeing any excessive load. So I'm at 60 volts. Fan is taking off. You can see the capstan flywheel is spinning. I'm at 90 volts. Okay, I'm going to stop at 100 because we still have a mystery as to whether or not this is operating at 100 volts or 117. I'm kind of the opinion that it's 117. Brakes seem to be in pretty good operational condition because when you spin it in the direction that it's supposed to be going, but then you try to turn it in the opposite direction, there's more friction, which is typical. And if the brakes are really that tight, I don't think I'm going to be using any 1mm tape on this.
I wouldn't expect that at all.
Okay. First of all, it's fired up. I don't have any smoke coming out of anything. Okay. There is a little unspoken of. See, that tube is basically room temperature. Okay. This one's a little warmer, but not hot.
So why are you checking temperatures? What's the significance of this?
Well, because in something this old, capacitors tend to get leaky. And when there are capacitors that are used to couple one stage to the next in the amplification process, you go from one tube to the next tube to the next tube, and you're going to have capacitors to do that. Older capacitors get leaky. Now, they're supposed to block the DC high voltage coming off of one tube going to the next. And when they get leaky, they don't block the DC like they're supposed to. And what they do is they end up over-biasing the next stage of amplification. And consequently, because that tube is over-conducting, it gets real warm. And it gets warmer than it should have. These tubes, except for the AUs, are virtually cold. Oh, you had it powered off.
Yeah, I just turned it off because we didn't
Okay,
lubricate
all
the
right.
motors.
So it's colder than it was. So rule number 1 in engineering and troubleshooting, you ask yourself, what's changed? Okay, and that will lead you to the solution. So, so this thing is not fired up. The power light's not on.
One thing that I mentioned at the early part of the video was it has manual tape lifters.
Yes.
So the way you do that is you do this.
Okay, so these things actually move into position when you open the door.
Right. So right here are the lifters for the tape heads. Because if you had the machine like in operation when you're shuttling tape, it'll actually be playing back the audio.
Yeah, and of course at high speed it's going to really wear the heads down. Mm-hmm. But what I'm also noticing is that this thing looks to be cracked. Okay. Now, how on earth would that happen?
Is there something that's supposed to like go in that little like semicircle there? Okay, wait, you know what that looks like? Hang on a minute. So the guy that I bought it from left me a little Ziploc bag.
Yeah.
And he said, I found the crystal rod in the box. It may be part of the transport, not sure. Is that what he's talking
Wait
about?
a minute, this little gizmo here is going to go in that little groove there. That way the tape comes in contact with this instead of this metal piece. And I do think that that's metal, but it's what we used to call Japanesium. It's like pot steel. It's very low grade steel, and that may be why this is cracked.
Okay.
But now this tape lifter is actually mounted to this door.
Yes.
So they're actually moving out of the way when you basically load the tape in here into the tape path, and then you close this door. A couple of things happen. Okay. First of all, the lifters move out of the way, but then these little covers actually create a seal, sort of a magnetic seal around the heads in order to reduce stray signals, noise, RF, and things like that. I'm concerned that there's only one crystal here. This is clearly going to need 2.
Gives us a chance to look at the heads anyway.
They don't look worn. Oh, but there's absolutely no catch on there. Fingernail test. You can't feel a lip on there that's been worn by tape passing over the head. You're never going to start to feel a groove like that until you get past about 80 to 100 hours of actual runtime. So this has got to be less than 80 hours. I think it's probably closer to 15. This is in really good shape. Erase head, record head, and the play head.
Here's something that might be interesting that I recognized about the RP unit.
Okay.
It doesn't say left and right whenever you're choosing what input to record.
Yeah.
It says...
You know why?
Why?
Well, because they hadn't really decided which was left and which was right. How about that? Okay. But looking at this, what do you see?
Up and down.
I see an upper channel and a lower channel. Oh. This is going to be a cakewalk to work on. Famous last words.
Oil caps.
Yeah, that's probably something we want to be careful about. Oil capacitors from this vintage, the oil in them could very well contain PCBs, which is a carcinogen. I know when I worked on a number of vintage broadcast transmitters that the capacitors, of course, extremely high voltage, they would be oil filled.
So right away, I see a problem.
Which, more than just one?
Right here.
Oh, that.
Do you see what's wrong with that?
Well, not just by looking at it, except that it's slightly discolored.
Yeah.
But it's coming pretty much raw off of that high voltage to that resistor, and it's been hot.
Yeah.
So the question is why? Whatever's going through that resistor, current times voltage equals wattage. And the thing is, after 60 years, I might expect that to be discolored, but there's no evidence on this unit that it's been operating for thousands of hours that it would have done that over time. So I have to be concerned that something has happened recently that would have contributed to that. Okay, I'm at 60 volts. Okay, the motor's starting to turn. 100 volts. All right.
Tubes are biasing. VU meters are changing. I thought the left channel was a little bit louder than the right channel.
Well, it wouldn't have been loud exactly, because it's just basically the DC voltage between stages wherever these VU meters are tapping the signal from. There was just a DC differential that basically the meter interpreted as a signal. And I mean, most tube equipment will behave like that, okay, because as the filaments warm up the tubes, they begin to conduct, but the next stage may not be actually getting that signal yet, so because they're still warming up. Okay. So what happens is that you get a different DC differential going. The playback volume control, wow. Oh, okay. Well, I can tell you what that typically means. That meter is going to be probably after the second stage. Let's see.
Wait a minute.
Pots do get scratchy and they crackle and so forth like that, but you hear that in the signal. The fact is, though, this thing is pretty, I mean, it's been powered up for now almost a minute, okay? Yeah, it's still doing that. So there's something going on there where the signal that is going through this pot onto the next stage has got a DC differential on it, and the pot is simply wiping between the two, and it's registering as an actual signal. That doesn't have to be, just because the needles are dancing a lot, doesn't necessarily mean that the signal is really, really strong. It's just that it's enough in the milliamp or microamp range to actually be displayed on a VU meter. You know, I'm looking at these capacitors. Okay, now this all looks to be original. I don't really see this as having been worked on. I mean, even this little cable bundle here that's tied up. I think what I'd like to do is to just check some voltages. Okay, I mean, you know, you've got me thinking now that, you know, there might have been a signal on there, but I mean, if, for example, if there was some kind of bad filtering going on and there was some hum involved, then it should show up on the meters, or at least be detectable. All right, so now we've done the unboxing and the evaluation. You know, we set it up on the bench and we hooked it all up and we applied voltage to it slowly, you know, so it doesn't go up in flames. But now we have to do the investigation. I want to see, now that I've got power applied to this thing, that I'm going to actually take some voltages and just see how this thing is behaving. The thing I want to really bring to your attention is that when I read the voltage on a lead on a capacitor and then go to the matching capacitor in the other channel, the voltages should have been the same. And they're not, because the leakage through these capacitors is dragging down the power supply. So the voltages are going to be all over the place. They should virtually match, you know, within a couple of tenths of a volt, but they don't. So this is already an indication that this thing is going to have to be totally recapped. And in order to basically walk you through that in this investigation process, we have to go back to the lab.
Your main objective with checking voltages right now, where are you going to go first?
I'm going to go right to the source, okay? I'm not so much interested in the transformer yet, because that's, of course, where the high voltage AC is coming from. The high voltage AC coming off of the winding, if you will, is going to the rectifier tube on the plates. So ultimately what we want to look at is the cathode. And with a 6X4, the cathode is common. I'm doing this because that's the cathode, and it's got a plate and a plate with the cathode passing between them. So you got high voltage AC here and here. It's basically a full wave rectifier diode. What it's doing is it's basically energizing one plate, and the sine wave goes the other way, energizes the other plate. So we end up with a high voltage ripple coming off the cathode, which goes to the first capacitor. In fact, you pointed out this which is kind of cool, and because it's on, I'm not going to be sticking my fingers in here exactly, but you've got a ground rail that runs through everything here. So the chassis is ground, but it has a rail up here that's basically chassis ground throughout, which is convenient. The rectifier tube is right here. It's a 6X4, and it's a 7-pin tube. The filament wires, or the low voltage AC, if you will, for the filaments is actually these blue and white wires. You'll see those throughout. If it's a blue and white wire, then that's the filament voltages. One thing that I have also noticed is that, yes, okay, there's a 6x4, but the rest of the tubes in here are 12 something, something, something. Well, 12 is supposed to indicate the filament voltage, but the filament voltage throughout this chassis is only 6 volts. So you're thinking, okay, well then we've only powered the tube to half voltage. Well,
I think I know what you're looking for.
yeah, I'm looking for those schematics. These came out of my RCA vacuum tube manual from long time ago.
Yeah, right,
that one right there. And what's really kind of funny, if you will, is that the book is broken. Okay, I haven't got any bookbinding tape to take care of this, so I've been taking very, very special care of this. What year was this? November 1966.
Yep.
The book breaks in half, okay, because it's just wore out, but it was turned a lot to this section of the book. Well, as it turns out, this section of the book are the 12 AU7, AT7, and the 12 AX7. 12 A something tubes are everywhere. So what I've got here is basically just a schematic. The schematics are identical, okay? It's just that the 12 AU7, as I might have mentioned earlier, is a medium amplification factor tube, medium, okay? Which means the gain is medium. But the 12 AX7 is a high amplification tube. And it's not surprising that it would be at the beginning of the input to the circuit throughout, because the first stage in most any amplifier is going to be the highest gain of any stage in that amplifier. The idea being is that the more you're going to get more noise with more amplification. So they put that at the beginning of the amplifier stages, and it gets less and less, still increasing, but less with less gain. And what happens is that the noise that's generated, you wouldn't want more noise generated at the output of the amplifier than you would at the beginning. Okay, well, the amplification factor for a 6AV6 is 100. So, as I said before, the first stage of gain is going to be on the order of 100. Each subsequent tube is going to be less gain, but still providing some amplification. Okay, confused? Well, that's what the rewind button is for. Yeah, like I want to listen to that again. What I want to do is check the voltages throughout, because that can be very telling in a circuit that is this old. So looking at the meter, ground wire is attached. What I want to do is first look at the output of the tube, the rectifier tube, and in this case I've got 292 volts DC. Now it's going to be attached at the other end of one of these wires to the capacitor. The voltage coming off the rectifier tube is going to a capacitor, which is basically filtering that with a reference to ground. The next thing it does is it goes off to a dropping resistor and then doubles back to the other capacitor in the same can. So what you end up with is what's called a pi filter. You've got a capacitor, a resistor, and a capacitor. So it looks like the letter pi. And that's where it gets its best filtering, because as you add capacitors to the power supply, you filter more and more of the AC ripple out of the DC. Case in point, let's just take a look here for a second, okay? There is the 292 volts DC, but the AC on that line, it's below the ability of this meter to read it, which means that filter cap is doing a pretty damn good job. So that's going off to a resistor, and it comes back to this capacitor. There's no AC on that, but it's also dropped down to 246 volts. This is going to be the first high voltage source for tubes in this amplifier. It's fairly clean. Goes through these resistors, and there's actually 2 resistors coming off of there. Each subsequent dual capacitor in this circuit is going to have a lower and lower voltage. The DC is already clean, so that's actually a pretty good sign. After these first 3K resistors, well, they're going to be going to different plates in different stages of the amplifier. Okay. And we can figure that out by going to the plates of these individual tubes. What I wanted to get through the circuit this way, and then look at the actual plates on the tubes and see how they're behaving. This is the next stage. That's 207. This is after the first dropping resistor and the second dropping resistor. Okay, so we got 206, 207 there. Okay, and then this next capacitor down here after, see, what is that, a 30,000. Okay, so now the voltage is at 117 volts. This is the end of the line for power, and that's 85 volts. Now, we're gonna go backwards now, actually forwards. We've went backwards through the power supply. Now we're gonna begin. Wanna look at this first stage. Or actually, there's gonna be another resistor right here, 100K. All right, so that last capacitor in the power supply was 85.5, but the plate voltage on this first tube, which is gonna have the most gain, is 56.8. This tube has actually got 2 triodes in it. It's a 12AX7. Pin 6 is the plate. So that's the DC voltage, about 57 volts on that plate. And then this plate over here is 60. So 56 and 60, pretty close. All right, and really the only fix for that is to just tweak the resistor going from the power supply to that plate. But I really don't see that as an issue right now. But now this should actually have no DC on it. I've almost got 1.5 volts on there. I'm sorry, that just shouldn't be there because the input to that second tube, it's got an impedance resistor on there, 300K. Consequently, you know, that means that there's at least 1.5 volts across that resistor. I mean, there really shouldn't be any DC on there. That tells me that with 1.5 volts on one side and 60 volts on the other side, that capacitor is leaky. Let's check this one. Okay, same thing, stage 1 to stage 2, 57 volts on the plate. This should have 0 because it's got that resistor to ground, 1.7.
Capacitor
But
strike again.
I'm not surprised.
Okay.
I'm not surprised. Something this old, yeah, the capacitors there are leaky, but it also didn't go up in flames when we fired it up. And one good thing as well, because I'm going to take this tube cover off. The tube, even the first or the second stage, the tube, I can hold my hand on it. So it's not so bad, but tubes that have too much DC on the grid is going to over-bias, or maybe under-bias, depending on how you look at it. That tube should be at near cutoff. And with a positive voltage on the grid like that, it isn't. It's not going to be there. So, and that's the beauty of this circuitry, because this is like you can get to everything. Replacing these capacitors is going to be a cakewalk. Let's just check the stages of the playback amp, just for shits and giggles. So this is the plate of the second stage, second tube, 45 volts. All right, that's nominal because it's going to have less gain, so it's not going to have as much voltage on the plate to get it to work. But what's coming out of that capacitor to the grid of the next stage?
I'm going to say 1.8.
1.8 for a leaky cap with a 45 volt input?
Okay, fine, 1.3.
All right. I don't want to discourage you.
All right.
All right. But the capacitors going from stage 1 to stage 2 are 0.05 microfarad. From stage 2 to stage 3, they're 0.1. Okay. Now, that is closer to 1 microfarad than 0.05 is. 0.05 is here, and 1 microfarad would be there. Okay. But 0.1 to 1 is going to be more like this. Okay, so what happens is that, okay, it's technically a larger capacitor. So a larger capacitor, if it's leaky, is going to probably have more leakage.
Okay.
Now, that said, now what do you think the voltage is?
I'm going to say 9 volts.
Which is why I don't give them an allowance.
I don't know numbers.
Okay, again, 45 volts going in. Okay. You want me to guess?
Sure.
I'm gonna say close to half of that. I'm gonna say 22 volts. I'm gonna say 22 volts going to the grid of that next tube, which is, it's on the verge of dangerous because the tube is probably going into saturation. Okay, so here we go. Coming out of that, 21.5.
Okay, fine. You know what you're talking about. That's why I'm not speaking very much right now. This is like way out of my element. All I'm thinking of is the fact that this...
I know what you're thinking of. You're thinking that, hey, I'll get Dad to fix this thing, and then when he's not here anymore, it'll be mine.
Halfway correct. Hey, I'll get Dad to fix this because I don't have the time to do so.
Well, yeah, Dad's retired, so Dad's got time, huh?
Yes.
You know? So if I had all this amount of time, then why is it I'm the one who always has to put the trash out by the street? Just asking. Okay, so that capacitor, let's look at this one over here. Okay, basically the other triode in the same tube, it has a plate voltage of 39.4. Okay.
The other one's 42, yeah?
This one was 45. Okay, so that right there should tell you something.
All right.
Okay, these capacitors being leaky are dragging down the power supply.
Yeah.
Okay, we need to fix it as soon as possible. So this one, what did we say? 39.4.
What microfarad is it?
It's same. I mean, It's basically 0.1 and 0.1. This was 0.05, 0.05. This is 0.1, 0.1, going from stage 2 to stage 3. Okay, so the capacitor on the grid of the next stage, stage 3, was half of the voltage going in. So if that's 39.4, you think, you know, depending on how leaky it is, it doesn't have to be as leaky as the other one, but I'm going to guess 39.
39?
39, because it had 45 on the other one, 39. So I'm going to say 17.
I'll do 17.2, Alex. Or Bob Barker, right?
Yes, it's going to be the closest without going over.
That's right.
Okay, let's see what it is. 26.
Oh my God.
So you still win because you got closer than I did, but 26 with 39 going in, that's
a bad cap.
Yeah, bad, naughty. Stand in the corner. Okay, so that's going into stage 3. Okay, stage 3 to 4 is plate voltage right here. Don't worry about it.
You got audio hooked up.
Yeah, it's basically saying, hey, don't touch me there. Okay, so I've got 77 volts on the plate there. Okay, and so this is going to be the other channel at 75. So at least 77 and 75 is close.
Sure.
That should be good for something, right? Well, let's find out. Now we said what?
77.
77. And this is going into the last stage, 62.
Now this isn't going to affect anything plugged into it like these speakers, right? Because these are active monitors.
Well, you know, that's a very good question. I mean, if we were actually
DC
pumping
offset,
raw
right?
DC into these speakers, that could be an issue. Well, let's just check that real quick. Let's look at the output and see if there's any DC on there.
Okay.
None.
Oh.
0.015.
So there's a capacitor doing a lot of heavy lifting right now?
Yeah,
on the near end circuit?
on the very end, which we haven't got to yet.
Okay.
Okay. And then the other channel is 0.03. So
wow, that's really good in comparison to what numbers
that's
we're
really
seeing.
good. So yeah, we probably should have checked that before we hooked the speakers up. Okay, and they're powered speakers, by the way. You can't see them because they're over here out of camera view, and we don't advertise for Rocket. So now this last tube, I'm just looking at this. This is wired differently. There are no capacitors coming off the plate to couple the audio out. It's just basically power supply DC going to the plates. So that 212 volts on the plate. And of course, it's hardwired to the other plate, so it's going to also be 212 or within a couple of points. 212.
Spot on.
Okay, well, what's happening here is that last tube stage, those two triodes that are in there, are actually what's called a cathode follower. So instead of using that tube the way these other tubes were operated, schematic, okay, where in a typical triode, we'll just talk about one side of this, the plate is usually going to have a high positive voltage on there. The grid is usually biased to below 0, okay, in order to get the tube to cut off, depending on the class of amplifier it's operating in. But if you take and put no voltage on there, none, then current is going to flow. It's going to want to flow with a high potential like 200 volts on the plate. You're going to want to get some electrons flowing off that cathode to that plate. But what you have to do is to get it to shut down just enough to where it doesn't conduct. So you put a slightly negative charge on the grid and it will actually cause the tube to shut off. Unless you're going to operate in a Class A, I think I'm getting this right. But if you're going to operate in Class A, then you might even put a slightly positive voltage on there, and it's conducting all the time. That way, when you apply the actual signal to that grid, then the tube is going to be operating in the linear portion of its curve. In looking at
I'll scan
this chart right here, depending on your plate voltage, and then the plate current, if you will, is going to be determined by how much grid bias you have or don't have. All right, grid voltage is here, -2 volts, -4, -6, -8, so on. Okay, you notice how it's really a pretty decent straight line with 0. Remember, I said that the tube will conduct with no grid voltage on there. So it'll want to do that, but it's going to be kind of hard to control. So by applying 2 volts negative to the grid, then what happens is that the tube is going to behave with a certain kind of plate voltage, and we're operating, what do we say, 212, so it's going to be in this general area here. Let me get my 6R pointer. Okay, so at 212 volts, we want to operate in the linear portion of this tube characteristic. A certain part of this line is actually going to be fairly straight. That's where we want to be, because when we bias the tube to a specific spot, if you will, then any amplification that occurs with a signal on there, tone or music or whatever, okay, it's actually going to be rising and falling on that linear portion, and that you don't want certain signals to be louder than others, so you want to try to operate in the linear portion of the tube. So 212, we want to be in the linear portion, so really -2 has got a fairly linear portion at 212 volts on the plate, okay, and we can operate in that range and draw between 25 and 30 milliamps. So
And how do you read the milliamps on a tube then?
well, in order to know what the milliamps is on a tube, you'd have to put a meter in the circuit. You'd have to lift the lead off the power supply to that tube, put a meter in series with it, and then you could actually read it. And if you want to get it really, really accurate, that's the way to do it, okay? But then you've got to have the ability to be able to change the bias so that you can control to get those plates dead on, okay? They never really intended that. They just want to operate in the linear portion, and if you can get the gain structure right, it's going to be fairly accurate across the board. So, you know, and when they talk about, you know, the, you know, with the frequency responses, you know, and it's flat from 20 to 20K, plus or minus 5 dB. Well, you know, flat from 20 to 20K sounds really, really good, but not plus or minus 5 dB. It's going to be all over the place, all right? The typical human ear can hear the difference between 3 dB. It's like, play it 7, okay, play it again, plus 3 dB, I can hear that, okay? A trained ear can get down to 2 dB difference, sometimes 1 dB difference. Would you care to speak to that?
I used to. I don't know if I can do that anymore.
What?
Exactly.
So, in any case, that's what you're going to be achieving with the tubes. But, so, I really got into the weeds on that. I'm not sorry, okay, because in some cases it's important.
We're trying to give you content that you don't often see in other places.
Well, okay. So that almost sounds like a microphonic tube, but it may just be a loose connection on the tube.
What tubes are? We'll find out later, but I wonder what tubes are in this thing.
Oh, you mean what brand?
Yeah.
Well, I don't know.
Shall I turn off the unit, or?
Huh?
You want me to turn off the unit? Oh.
Why?
Okay.
It's that's what I think.
Japanese.
It is Japanese, but it says Matsushita.
Oh, Panasonic.
Okay, Matsushita Electric Industry Company Limited.
So they got Panasonic tubes in a Denon player. What's
I don't know. It's all Greek to me.
It's Japanese, not Greek.
Oh, okay. My bad. So, okay. So let's see if I can get this back in there the right way. Okay, that's the volume control on the output. Okay, but here's what's interesting to note. Okay, and that is I'm cranking that knob back and forth, and it's not getting louder or softer, it's just making noise. Well, what we have there is an intermittent white noise generator. Okay, sounds like some of the 78 RPM records in my library. That's DC. So what's occurring here is that there's so much DC leakage in this amplifier that it's got as far as, well, the third stage of this amplifier. If it could be tone, it would be just a constant tone, but in this case it's just noise, the DC noise that's being funneled to the next stage. And
one thing that I noticed is it looks like the balance pot gets the signal first, and then it gets chained over to the volume.
yeah, that's a good point. Good call. Because the previous stage, basically the output of that through its capacitors that are leaky goes to the balance pot first, and it comes in on this side of the pot. This is the wiper, so this is the input to that pot. You notice there's no wire on this side, so it's really just a rheostat, okay? But the other channel comes in on this pot, so when this is turned counterclockwise, then the wiper on this one is basically at this potential, and this wiper is as far from this connection as possible. So to turn it back the other way, now this point is on the wiper, and this one is far away. Try to get that centered, so that way the signals that are coming into here are basically appearing at this yellow wire and the green wire, which go right next door to the volume control, and then the volume control wiper, which is also green and yellow in this particular case, is basically taking the signal, or the absence of it, to the next stage. The problem is that there's DC appearing at the balance control and then feeding the volume control. So there's already DC present.
So with all these capacitors on the playback section running into this and then the volume pot, there's no way to escape the DC from feeding into the outputs because the capacitors are bad.
Because the capacitors are bad, replacing capacitors, problem solved.
Yeah. But the thing is, though, is that we're not getting pure DC to the output.
At the output, but that's partly because that last stage, that 12AU7, is a cathode follower.
Okay.
Okay? Because the output to the speakers leaving this unit is not on the plate side with capacitors. And by putting full voltage on the plates for that particular tube schematic, these plates are getting full voltage, so they're pulling the electrons out of these cathodes here. The signal is going into the grid, and it's modulating that, if you will, and it's being amplified. Not a lot, okay? Because first of all, a 12AU7 is only a medium amplification tube, okay? But by the same token, all that's really going to be coming off of these cathodes, with capacitors, mind you, is just the signal. So even if it had DC leakage, it's not going to amount to much, okay? And in this case, hardly anything at all, which is in fact a good thing.
It's a saving grace.
Quite frankly, I'm impressed, because if I had to think about it, that's the way I would have done an amplifier. I wouldn't want to risk 200 volts going into my powered speakers.
Or your amplifier.
Or my anything. Fingers, for that matter. I mean, it'd be a bad day.
So we need
the output, which is going to be on the cathode with a capacitor coupling the signal out. So what is the DC value? Now, and of course, it's coming off the cathode, so it's not going to be a lot of DC voltage. All right, but I'm more interested in how much the capacitor is blocking the DC. And coming off of that cathode, 53 volts. Okay, and then this is the actual output.
Oh, okay.
0.02.
So that's a healthy capacitor.
Yes, I would call that a healthy capacitor, but it gets changed anyway. Okay, on this side, on this cathode, 36 volts. Now there's something very interesting. That's 36, 37 volts. But on this cathode, it's 54. It's almost twice as much.
Is that because the capacitors in the earlier stages are bringing the voltage down?
I wouldn't think so, but I can't rule it out. All right, but that is significant.
Yeah.
Okay, I'd almost be willing to put a microamp meter in there or a milliamp meter in there and just see where the current is going. Okay, but that is a factor. Okay, also it could be that that tube has just gone soft.
Okay.
You know, because it's just not conducting. So 37 volts, wow. Okay, and yet both plates are getting the same voltage at 212 volts. So let's look at schematic. Grid 1 is pin 7, and grid 2 is pin 2. So 7 and 2. So let's just look at the DC voltage on these grids. Coming in here, 39, almost 40 volts on the grid going to that tube. We're trying to figure out why the cathode current is so high. So 39 volts there, and that was pin 2. Pin 7, all right, that might explain it. The grid voltage is almost 56 volts on one and 39 on the other grid. All right, well then let's look at the correlation. Okay, if the grid over here is 56 and the cathode is 54.8. Okay, 55.8 on the grid, 54.8 on the cathode. Interesting. Grid over here is 39.6 and the plate is 37. So there's a correlation there. The amount of DC getting into those grids because of those leaky capacitors is causing excessive cathode current.
Ouch.
Okay, from the in that particular tube. So, and then of course the output. Fortunately, these caps are eliminating the DC coming off of there, so that the actual output of the last stage of the tube going to the powered speakers on one channel is 0.02, and on the other channel, 0.02.
Okay.
So those capacitors are doing a job, but I tell you what, they're taking a beating. They are really taking a beating. So they're going to get changed too. That's the playback section of this RP unit. It needs help.
So it sounds like I need to leave you with this unit.
Yeah, I mean, it's not like I had anything better to do.
Good. I figured you might enjoy this.
Well, I look at it this way. If I can get through something like this in a couple of days and have all of my fingers intact, I'm a happy camper.
Me too.
We've already done the voltage checks and stuff like that and determined that this thing is in major need of recapping. So at this point, I just want to do sort of a circuit trace through the RP unit and identify things that are going to, possibly throw me a curveball. Well, curveballs notwithstanding, this whole episode took a completely different detour. You'll hear me mention capacitor interrupters. Well, it's a thing. What I'm sort of curious about is, in looking at this chassis, and of course everything in here is point-to-point soldering, which is going to make it real easy to work on, because what I like to do is to simply trim the capacitor to be replaced right at the capacitor, leaving as much lead still soldered to the terminal strips and so forth. So I have a little bit of slack to work with, particularly because a lot of these capacitors in situations like this are going to end up being smaller than the capacitors that they are replacing, because technology has improved. They've managed to trim things down a little bit. In this particular scenario, things are kind of layered. You got a capacitor, and then you got resistors on top of that are going perpendicular, and then you may have another capacitor on top of that. You just want to give it a real good once over, okay? Maybe even a twice over. Something like this, you don't want to miss anything. Lo and behold, I want to point your attention to this resistor right here. That's discolored. I mean, it's got a very dark, toasty looking ring that's going around it right there. That means that puppy got hot, and it's rated with enough headroom that should not be happening, which means that something is drawing excessive current through there, and wouldn't surprise me if it's a capacitor. Again, resistors, typically, they really don't want to drift off of their value without some excessive amount of evidence, like lots of smoke. I think the thing that really helped save this from excessive damage is the fact that when we powered it up, we raised the voltage on the bench supply very slowly, so it didn't, hurt it so much. But let's go ahead and just check that resistor. Let's find out what we're dealing with here. 480. All right, so it's climbing. So there's obviously some capacitor involved with that. Now, one way of doing that is basically lift one leg of that resistor up and measure it outside the circuit. It's always a good idea to lift it out of the circuit, but we're on fact finding right now. So coming off of this resistor, what's going into this resistor is this brown wire. All right, so coming off of the full wave rectifier, which is a 6X4, okay, that's coming off and going to the filter cap over here, which is going to be a 40 mic at 400 volts, I believe. Okay, so that's the first filter cap, and then it comes off. That filter cap goes through the chassis to a wire wound resistor on the other side and then doubles back, okay, to this capacitor in the same can, which creates what's called a pi filter. So coming off of the vacuum tube, you've got a capacitor with a resistor, capacitor to ground. Okay, there's ground right there. Capacitor, resistor, capacitor. So it basically creates the appearance of the Greek letter pi. What I'm noticing is that brown wire, and I'm talking about going to this resistor, and that's the only thing it goes to, which means this is getting practically the full brunt of the voltage coming off of the rectifier tube. And what ends up happening is that it's coming off there, going to that resistor, and coming off of that resistor are two capacitors. So the current through this resistor is going through those capacitors, and from those capacitors, it's going to this oscillator circuit, which is for the AC erase and AC bias for the record head. So you got the erase current, you got bias current, and that's what's going on here. With paper oil capacitors, you just assume they're bad and change them, okay? But I think what's happening here is that there's too much current going through here, which probably means that these capacitors are passing too much DC. These two capacitors here, just by the way, are going to be your coupling caps that take the recorded audio portion and combine it to the AC bias for the record head. So these are coupling that, okay. A doorbell and capacitor interruptus. Excuse me. All right. I have no idea what the hell this is. Well, it's packed incredibly well. What the hell? Oh, wait a minute. Oh my God. Holy shit. This is an RP unit identical to the one that we're about to work on. Porn! Ooh, I bet it's even got pictures. You know what this means? Oh, got an extra pinch roller. I wonder if this has got the conversion kit. And the reason I say that is because this looks like, right there, Denon. And it's all in Japanese. But even then, even with Japanese, okay? Kilogram is still a kilogram. May not know what this says, but it's 70 kc. Okay, that's going to be the bias frequency. So what happens is kilocycles and kilograms and all that kind of stuff, numbers are going to be the same numbers. Numbers are numbers are numbers, all right? May not know what the words are, but we can figure it out, okay? Heck, nowadays there's probably an app for my phone. Okay, this is no doubt the owner's manual because it's got the pretty picture on it. See, like that, transport. transport. Oh man. You don't suppose. Man, you gotta see this. I mean, this is incredible. I mean, with wrapping all the way around, bubble wrap and everything else. Wow. Check this out. And this is in such great shape. Now, he said nothing to me about this. He said, not word one. There were two boxes. The big one and this little one. Hang on a second. And that's Denon. That's the one that was manufactured and released specifically for the market in Japan. Okay, again, in the early 1960s. Okay, so this is instructions. This says it's instructions. Maintenance. I like to go to the end of the book and see how it ends. Schematics. Anybody? Please, 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 please. Schematics, perhaps? Okay. All kinds of mechanical parts are listed. Again, mechanical parts. I mean, if there's schematics in here, that could very well help troubleshoot so much of this. Yeah, decrease, increase, brake tensions, solenoid travel adjustments. What is this? Okay, it's talking about switching from 50 cycles to 60 cycles and changing the capstan capacitor, 1.5 mic to 0.5 mic. Okay, well, I'm not seeing a schematic yet. And even if there isn't one, we can get by. We can figure out where all of the gazintas and gazautas are. And this pinch roller, a 50 cycle electrical system, the capstan would be spinning at a particular speed, but it would be slower than in America, which is 60 cycles per second. Our electrical system, 60 hertz, okay? And if you've ever grabbed a hold of a naked extension cord, you know how much it hurts. What is in here? Denon tubes. Ta-da! Denon tubes. They're all individually wrapped here. Look at this. Holy cow. Hang on. Seriously? Big mystery. Well, I'm going to try to solve that mystery. Some of you may recognize us. I am curious. I mean, what could possibly be on here? I mean, come on.
Good morning, Mr. Phelps. The package you've received contains a vintage high-fidelity stereo tape deck, originally branded as Denon, manufactured in Japan in the early 1960s. The production of this device mirrors the same techniques and components as the Griffin tape deck that now graces your laboratory workbench. Your mission, should you choose to accept it, is to bring either or both of them to operational fruition. In so doing, identify dissimilarities, if any, and all while bringing definitive 6R principles to bear. As always, if you or the 6R budget are in any way compromised in your undertaking, the Secretary will disavow your attempts, and you will be responsible for costs associated with return shipping. This tape will self-destruct in 5 seconds.
Oh, shit! What we've done is a time lapse of the actual recapping process of the RP unit of this Griffin and its transport. And we're going to special treat. We're going to actually leave the time code on the screen to give you some idea of why it takes me 6 hours to get anything done. Okay, this is going to be fun. All right, enjoy. I want to show a little bit more detail, maybe a lot more detail. You know, I love living in the weeds, okay? You know what I'm talking about. Well, in this particular episode, I want to show you some of the techniques that I used in replacing the motor caps. I'm even going to go into a little bit of detail, all right? That my producer's shaking his head. No, he don't want that. But we're going to go into some detail about the hysteresis curve that's used in these motors to provide additional torque, okay? Because a lot of people think, well, you change the value and you get more speed or something. No, I'm going to try to explain to you why they use capacitors on certain motors to provide additional torque. And it's real important. And I wanted to show you some techniques about how to use contemporary capacitors to replace the old oil can capacitors that were used in the motor in the first place. All right, so let's take a look at that. Motor run capacitors. Going to be swapping those out. Here's what we've got, okay? These are AC motors, so we've got voltage and we've got time. AC signal goes into the motor on a winding, okay? So we've got basically a sine wave, which is a beautiful thing, okay? And these motors have more than one winding. So what happens is that the primary AC signal goes into the motor and it starts that motor up. The thing is that we want to be able to increase torque, not speed. Motor run capacitors are not about RPMs, okay? It's about torque, okay? So what happens is that a winding is getting a principal AC signal, but one of the leads of that AC is actually going through a capacitor. The value of the capacitor is going to be specifically for the phase differential of the winding, depending on how the motor was actually built. Inside the motor, there's going to be all of these poles. Each of these poles is going to have a winding on there. And that's how the current through the coil is basically on a pole piece that attracts a portion of the armature. The armature is the part that spins, the stator is the part that doesn't spin. What happens here with an alternating current is that one wire is going to actually go right to this winding, okay? But there's going to be another winding, a second one, which I don't have room for because I draw so big, okay? And then what happens is that has a wire that comes off and it goes through a capacitor. And by virtue of the capacitor, the AC signal is late. It's delayed because the voltage going in is here, but the capacitor voltage is there. So it's later. So what happens is that you end up with another sine wave, okay, that's late. But this goes to this other winding, which is just a little bit after that winding. So you had like, let's look at it this way. You got 12 o'clock, 3 o'clock, 6, and 9. 12, 3, 6, and 9, all right? But there's a winding going to be at 1 o'clock and 4 o'clock and 7 o'clock and so on, okay? Because I forget what comes after 9. And the capacitor is sending that signal to that winding. So as the armature gets that first voltage, it wants to take off. But the next pole is going to have a slightly delayed signal voltage on it, which is going to then add a little bit more torque, because if you only had 4 pole pieces, 12, 3, 6, and 9, then what's going to happen is that it's going to goose that motor, but it's going to start to slow down a little bit until it starts getting to 3, and then 3 is going to pull that across, and it's going to send it on to 6, and it's going to send it on to 9. But what happens with a second winding, you get added torque and a little bit more speed consistency. That's what these motors are doing. And these motors are going to have capacitors in there really just to maintain accurate torque, okay? Now, the capstan motor is going to be the most critical of these motors and the motor capacitors, because you need a very, very accurate speed control, because naturally the speed of the tape has got to be consistent. So that's important, and that's why the capacitors are there, okay? Now, these capacitors, they're oil-filled capacitors. Now, after they have filled this can up with the plates that will comprise the capacitor, they fill it with oil, and then they solder this shut, okay? And they do the same thing to this. So when you see these rectangular looking capacitors in a machine that you're working on, That's the best way to be able to tell. What I want to do is I want to replace these capacitors. And we're going to do that. But yeah, okay, these are really, really old. And back in the 50s and 60s, I mean, there wasn't a large market for ceiling fans. Ceiling fans are no different than these motors, okay? Now, ceiling fans are going to be operating at a much lower RPM, so the windings that are in a ceiling fan are going to be configured completely different from these in order to get the low speed, but you still need the torque to get the motor to start. So they use capacitors. Well, lo and behold, capacitors for ceiling fans are perfect for this. And these capacitors that are in here are 2 microfarad and I think 250 volts. So they're not overrated by a whole lot. These capacitors are rated at over twice that. These are rated at 450 volts and 2 microfarad. And it's already half the size of the capacitors that I'm going to be working on. And they're cheap. My God. I mean, I forget. But I mean, I think if you're spending more than $9 a piece on these things, you're being had. I do want to talk about, just briefly, this capacitor here is actually got 2 capacitors in one can, which justifies why it's a little bit larger than the other 2, okay? Because there's 2 capacitors in here. Now, there's a common point between the 2, and then there's a capacitor pole piece lug down here. That's 1.5 microfarad, okay? And then there's another lug up here, which I have removed, okay? And I taped that up. I mean, I could just break that wire off of there, but I like to try to keep things as original as possible, but safe. So this lug up here has got no wire on it. That's because this was marketed for a non-Japanese market, and they operate at 50 cycles per second for their electrical system. We operate in America at 60 hertz, okay? If you get your fingers across them, trust me, they both hurt. You would actually use a jumper to go to this lug to add 0.5 microfarad to the 1.5 to get that motor to have the proper amount of torque at 50 cycles per second. If you're operating at 60 cycles per second, you cut the wire, okay? That changes the torque of the motor, not the speed. And you're thinking, okay, well, 60 cycles per second is going to be faster than 50 cycles per second, so that's for speed. No, it's not, because inside, on the side that you're looking at, right here, inside here you pull this faceplate off, and on the capstan motor shaft is a sleeve. This right here. Now this has actually got a stamp on there, and I don't know if the camera will pick it up. Maybe if I hold it just right, but you can see that's a 50, okay? So this sleeve gets put onto the capstan motor shaft. This diameter here for the actual belt from the motor to the capstan flywheel actually wraps around here, but the 60 cycle version is smaller than this. In order to get this to operate at the proper speed at 50 cycles per second, you have to use the extra sleeve, okay? So you add a capacitor to this, because 1.5 plus 0.5 is 2. The fun part is going to be getting these capacitors in place of these. These capacitors, these 2 mic, have a mounting lug. Since these capacitors are basically held in place by clamps that are screwed to the frame, I can take this loose, use one of those screw mounts for this lug, and then just basically splice the wires together. Solder those in place, wrap them with heat shrink, and pretty much be done with it. All the other caps, the oil paper caps, have been replaced. This electrolytic, which is a DC filter for the relays that are in here. That solenoid there is for the pinch roller, basically just, engaging the pinch roller to the capstan. This solenoid here is for the brake release. So the brake bands that are going around these reel tables are controlled by that. There's a mechanism in there that releases both of them at the same time. So that's a wonderful thing. with no further ado, let's go ahead and get some of these capacitors replaced, because I really want to put the juice to it and actually start playing some of my old music. This capacitor had clamps that kind of held it in place. So I'll use this clamp, this mount, for this capacitor, but I have to make it want to hold it. So I'm going to leave this excess up here because this side is going to be sticking more to the capacitor. And I'm going to mount it in there like this. I want the wires and this tab to be toward the right. I'm going to put a cable tie on there. Simply going to snug this up on there and move on. The splice I'm going to make is probably going to be in the neighborhood of 1/4 of an inch. So I'm going to use maybe just a little more than 1/2 inch of heat shrink. I'm going to run this down onto these leads. Sometimes it's a good idea to go ahead and tin the wires if you're using stranded wire. .5 and 0.5. When I install the new capacitor, I won't include the jumper hanging loose because there's no point. This is going to be fun because of these brackets that are meant to hold this oil-filled capacitor. This is going to be fun because this capacitor here is so completely not the dimensions of this one. You know what? That really wants to hold on to that a little bit, so that might be a good thing. But this bracket up here, it's just too cramped up in there to try to put a capacitor in this space up here. So we use this bracket. Now these wires here are going to be spliced onto that, so I'm just going to put that bracket between the leads of the new capacitor, but I'm also going to put some double-face tape on there. Now, I will go around this with a cable tie. Because of the geometry of this capacitor and the smallness, the narrowness of that bracket, the cable tie is not going to really want to hold on to a whole lot. It's going to be good for another 60 years. I always like to do the heat shrink first thing. All right, we'll tin that before I strip the yellow end off, because stressing that wire, trying to get the insulation off that yellow wire could affect these twisted together before I get them tinned. And I'm seeing just a little bit of excess stuff up there. Green is by itself on the lug with black. Just going to put the double-face tape on there and a cable tie. Okay, I'm going to just snug this up just a little bit. I'm going to loosen it back up as I put the cable tie on there, so that way I don't stress it and accidentally rip it off. I like to just pull that off just a little bit and then twist while the insulation is still on there. And it sort of just cleans that up a little bit. We're going to look at the voltages of all of the different stages and all of the different components, tubes, capacitors, resistors, things like that, But we're going to compare that to the voltages and stuff that we had in part 2. And we're going to see how much better it is operating now. Now, we don't have a service manual, but we can use the tube manual to make sure that the tubes are getting the voltages that they're supposed to be getting, and that we can then assume that they're going to be operating correctly. All right. And the reason you want to do this is because when you want to check different functions of the unit, you can't really figure out whether it's operating correctly, because the problem is that when the voltages are all over the place, you really can't determine if it's operating correctly. So in order to avoid any surprises at the end, we have to be able to make sure that the voltages are correct at the beginning. Let's take a look at that. Got the transport here. We've got the RP unit that we're going to smoke test, and then I've got a spot right here for a fire extinguisher if it's necessary. This is the record head and the erase head. This is the transport control. I'm not going to do the playhead because we haven't fixed this yet. The connector that we are going to end up using, which is a direct mate for the RP unit, is actually a 4-pin cinch Jones. I want to just bring this up very slowly on power, and just enough to get the filaments warm enough to conduct. I want to see it actually survive the initial power up. Let's go ahead and monitor the high voltage. Talk about being gun shy. I'm also spark shy. All right, so that's 135 volts. That's coming raw off the full wave rectifier. So now I'm going to gradually raise the line voltage. So it looks like it's surviving. I'm at 80 volts going in now. 95, 100 volts going in. I'm not seeing any evidence of anything giving up the ghost. So I'm going to go to 115 because the readings that I took prior to recapping are going to be based on 115 volts line voltage. My prior readings on that particular point with 115 volts going in, I was getting 346 on that point. I'm getting 350 now. All right, so one can assume that there's less current draw. So now let's check out these two capacitors here. I'm going to go to this point, okay, 266, which was 256, and this side, which is 249. 249. The record section, the last voltage here is reading 136, used to be 128. And this was 90 volts before the capacitor changeouts, now 112. So the fact that the voltages are higher means that it's not wasting the current through the entire stages of this amplifier. So now I'm going to look at, this is the playback section right here. So this is first stage, second, third, fourth. I'm going to look at the plate voltages on these, the first 12 AX7. This is now 77, used to be 57. This plate voltage, 75, used to be 54. And on this side of that capacitor, 0. Used to be 1.6. Okay, so let me just clarify. All right, 4 thousandths, tens, hundreds, thousands. Tim, learn how to use the decimal point.
Hey, Tim.
One.
You know why you were getting those really small negative voltages on the grids of those tubes? That's grid leak voltage. You see, a tube works on the principle of thermionic emission, which means that if you heat a conductor to the point that it begins to glow, it will start to emit electrons in a cloud around it. This is called a space charge. Do this in a vacuum, as in a vacuum tube, and the electrons are free to move around. The heated element in a vacuum tube is called a cathode. If you place another unheated element near the cathode, you can then make a current flow through the vacuum by just connecting a positive voltage to the unheated element while the cathode is grounded. But if you leave an unheated element like those grids you were testing, not connected to any voltage source, then the electrons from the space charge leak into the grid and out of the tube. Since electrons are negatively charged, the grid builds up a negative voltage, and we don't want that. So a grid leak resistor gets connected between the grid and ground, and this kills almost all of that negative voltage, except for the tiny amounts you were measuring.
You know, that's a great point. And that also reminds me, long time ago, long time ago, one of my instructors was describing how current flows through a circuit. The thermionic emission, the cathode is heated, and as was described, the grid without any heat on it is basically just going to be a cold conductor inside that tube. The cloud of electrons around that cathode is basically going to get picked up a little bit by that grid and show up as a potentially negative value. Well, let's just look at this for a second, okay? That grid needs to be at a low potential. What ends up happening is that coming off of that grid is going to be this resistor to ground. What the instructor had shared with me is that, okay, current flows from negative to positive. Got it, all right. But going this way through that resistor, then this becomes the negative side, and then this becomes the positive side, making this grid and this connection, this becomes slightly more positive because the electrons are flowing. Now, I kind of disagreed with that at the time, simply because, well, if electrons are flowing through that, then wouldn't that be negative? Because electrons are there. Because of the current flow from negative to positive through that component, then that becomes a more positive potential. But then at the same time, this cathode, which is right here, grid's here, cathode's here, okay? Coming off of this cathode is also going to be this resistor to ground with a bypass capacitor coming off of here. And this capacitor then is a bypass capacitor on that circuit. And electrons are going to be flowing from negative to positive through this circuit to this point right here on this cathode. Well, in the case of this cathode right here, all right, the cathode with its resistor and its capacitor is actually 0.76 volt positive, mind you. Now, that's on the cathode, but let's just take a look at that grid. Well, the grid is negative 7 thousandths of a volt. So the cathode is technically more positive than the grid at this point. There's no signal going through it. It's just basically just warm, ready to go. And what ends up happening is that because that net voltage on the grid is more negative than the cathode, the tube is at cutoff. But by so little, I mean, just the minimum amount of voltage to get it to cut off, because the moment that you hit that with an audio signal, that tube is going to start to conduct and it's going to be amplifying the signal. And it does that through every stage of this amplifier here. Now, the plate voltage for the next stage used to test at 47 volts on this plate before, and now it's 107. Okay, that means that the tube is not saturated and it's not being dragged down by the next stage because a capacitor was like not doing what it's supposed to. This is 106 and it was 41 before, 106 after, and it's virtually identical to the other plate, which means that the left and right channels are going to be getting the same amount of voltage, which means the tube, if the tube is in really good shape, it's going to be amplifying left and right equally. And stereo, I mean, it'd be nice. It's not like you're going to be mixing a recording from the 1970s where you got everything over here and then everything over here. And it's like, well, we don't have to worry about capacitors because nobody's going to be playing audio on these things. It's going to be perfectly balanced. And it's like, yeah, well, again, 100 and, what was this one, 106? 106.7, okay? I'm guessing that this should be virtually zero, but we'll see. Well, what did it used to be? Used to be 28 volts. Now, it's like there's no DC on there whatsoever. This thing is going to be incredible for audio because it just wants to behave now. The next stage of this particular circuit is convoluted. It's just a whole lot of stuff going on right here, right now. pin 1 and pin 6. So if I can get onto pin 1, and do this very carefully, okay? So that's 103.7 on that plate, and then this plate here is 102.5. That's close enough. I mean, honestly, it's going to be close enough. But the beauty of this is now we look at what is coming off of the capacitor, the coupling cap. That says 52 volts, and it used to be 79. Oh, hang on, red flag. That capacitor is passing DC. No, it's not, okay? Because the next stage is a cathode follower, which means that the cathode, and hence the grid, is actually going to be well above ground potential, okay? And they're doing that because they want to decouple the cathode from any other circuitry that's in here. So that to me is cool. That's good. Now the last stage, the 12AU7, coming off the cathode is probably going to have a DC voltage on there of, 72 volts. But the output going to the output of this deck is 0.3. So capacitor's doing its job. Cathode on this one is 67 volts. And the output, that's doable, okay? And in the case of a cathode follower, what that really means is that the signal coming off of that tube that's going to be used for audio is actually coming off the cathode and not the plate. Helps if you pay attention to what you're doing. So 247 volts. So that's a relatively high voltage for that last stage. But again, they've put that tuned circuit in the cathode to raise the potential of the cathode up. So if you're already starting out, if you're not at ground, you're starting out at 51 volts, then you're going to need a much higher voltage just to make the tube conduct. So this is the playback preamplifier. This is the record preamp. Dual triodes, so you've got a left and right channel, left and right, left and right, left and right. It's dual triodes all the way through. One is for the left channel, one is for the right. Same thing for the playback, but I mean, this first tube, it's doing its job, but it's practically room temperature, okay? A little warmer than room temperature. This one is warmer than that one, okay? This one is warmer than that one, and that one's hot. But that's to be expected, okay? Especially the way that one is conducting. So it's all good. And I'm not even going to touch that rectifier tube because I know better. It's going to be hot as a 3-ball dog, let me tell you. You know what? Let's treat ourselves, okay? Taking a look at these meters, okay? This is still powered up. As I was pointing out before, in the before time, before we had actually changed out all these capacitors, when you would change either one of these record volumes, the meter would just dance all over the place because that pot was not just adjusting the audio signal, but it was also taking that DC component that the audio was riding on. And so you were actually varying between a DC potential, and the needles on these meters were just dancing all over the place. I'm cranking that knob back and forth, and it's not getting louder or softer, it's just making noise. But what we have there is an intermittent white noise generator. But I can do this, no activity whatsoever, but I can hear something. There is audio coming out of this, and it's pretty freaking clean, let me tell you. Now, I'm gonna just show you something, okay? I'm just gonna turn these up. Audio, okay? Oh, hum on that channel over there, okay? Now, I'm just going to warn everybody who's watching, I own the copyright on hum, okay? I can use hum and nobody can steal it from me. I own that. Not gonna use any music.
Help your body grow it, because it's never just about your hair. Calm. These statements have not been approved by the FDA.
MOUSE.
To diagnose, treat.
Okay. I can't get much more out of the meters right now because it's so freaking loud in here. Let me see if I can turn these speakers down.
So the brain and the body aren't communicating at 100% anymore, and you get a malfunction
He's been reading my mail. So that seems to be working just fine, but I'd like to feed it a stereo signal. So my producer has sent me a file that we can get away with playing through this and see it and hear it. And this is what I think we're getting. I gotta tell you, the ballistics on these meters are incredible. So I'll tell you that not actually trying to change any of the equalization switches on here, because the equalization switches are part of the playback. There is no real equalization going on into the record circuit. So it's whatever is going into the unit is going to be recorded onto the tape. What you do with it when you play it back is entirely up to you. Outstanding. This thing is, I think we're ready to take this to the next level. I would like to check the record circuit just for the erase oscillator and the erase current and the bias current going to the record head. I've got 0 dB on the meters, but the knobs, one of the knobs, the left channel is at approximately 11 o'clock and the right channel is at 12 o'clock. And I'd love to be able to show that to you. There. So what I'd like to be able to do here is to actually see what the levels are coming out of the outputs of this unit, because these switches here in front are for monitoring, and in the record mode, they're actually looking at the record preamplifier, and in the other mode, they're looking at the playback amplifier. Now, I don't have the playback heads connected just yet, so what we're hearing is basically what we used to call E to E, electronics to electronics. So it's basically the signal going in, going through the record circuit, and coming out, and that's what we're hearing, all right? What the meters are telling me is that at that middle stage that we talked about earlier, where all of the EQ and all that is going on in the playback part, is not going to probably be as accurate as we need it to be. I mean, I can measure the meters and, you know, the meters are going to say, okay, well, they're even. So, but what is the actual record level? Don't know that yet. So here's what we can do, which is going to be incredibly irritating. Basically do a tone sweep. And we can see how the meters respond to the different frequencies. It's a crude test. Okay, so not changing the pots. Let's see where we're at. Again, it's going to be really irritating. 15 hertz to 15K over 30 seconds. All right, here we go. Okay, much lower. .400 hertz. 1K. 2K. 5. 10. So that's where we're at right now. Is 1K. Just curious. Gotta tell you, these meters are tracking dead on with the pots at 11 and 12 o'clock, but it actually doesn't surprise me that it doesn't actually track just like that, especially when they put a balance pot on the playback side. I gotta tell you, I mean, it's just, I mean, on the one hand, yeah, okay, I want to be proud of me. I want to be excited that I did all the caps and everything like that and nothing went up in flames. But this is just so exciting to have this measure of success on something as complicated as this could be. And I don't want to blow my own horn, but what I'm really excited about is having done it, showed you how I did it, and then maybe you can come away from that with some insight into how you can do it yourself. Because the techniques and stuff as far as replacing capacitors is, you know, every bit you want to work on a guitar amplifier, you want to recap it, you want to, you know, deal with the tubes and stuff, and be able to understand how the tube is working and what the capacitors are actually doing and why, you know, and again, I have to stress this, that yes, you'll have a high DC voltage on one side of a cap coming off of a tube plate, all right? But when they're using a cathode follower and you see a high voltage on one side of the cap and a almost high voltage, maybe half that voltage on the other side of the cap, you're thinking, oh, the cap is bad. Those are important things to know, because that way when you understand how the circuit is really working, then you understand the behavior of everything that works around it. Remember when I said before, you know, about no surprises at the end? Wrong. -5. Thanks for playing. Ain't gonna happen that way. Because when I thought that this deck was, you know, should operate correctly, and then I started getting into checking some things, and things weren't where they were supposed to be, found out that there was some more stuff wrong. But again, until the voltages were correct, I really couldn't go that far. Well, now we got deep into it, and here's what that looks like. Don't have a schematic. There ain't gonna be a schematic. There probably aren't anymore. You know, it's at the bottom of somebody's bird cage by now. But the way this power supply is set up basically split the function of the power supply. It comes off the rectifier tube to the first cap, and then everything is pretty much just paralleled all the way down. And it's kind of cool just being able to look at the circuit. You can see what's going on. For the record, no pun intended, you can see how the signal is going from stage to stage to stage. That's what makes it so cool. I mean, when you can just look at it and it talks to you, okay? Sometimes they say bad words. Before I started recapping this chassis, I took a bunch of readings. Wanted to actually just sort of record what the voltages were at the various stages throughout the chassis prior to recapping it. And it's a good thing to do. I prefer doing that. Of course, the downside to that is that, yeah, the caps were pretty much toasted. This is where we're at. I took all those readings, and one of the things that I noticed prior to recapping it was that even when this was put into the play mode with no tape on it, just, you know, put into play mode, going to the record head and the erase head, I had a signal there. Yeah, it was 70 kilohertz, and so on the record head, which would have been record bias, there was 3 volts peak to peak going to the record head. There was 10 volts peak to peak on the erase head. And had I put a tape on there, and the worst case scenario would have been to put an alignment tape on there, because that record bias and erase current would have damaged the tape. It would have partially erased it, or maybe even fully erased it. In any case, now that it's all recapped, those signals aren't there anymore. The oscillator isn't on. So that's a good thing. But what we want to do now is to investigate something else that came up, because now that it's all recapped and you go to record mode, turns the oscillator on, there is no record bias for channel 2. Channel 1's there, 34 volts peak to peak on the record head for bias, and I'm getting 155 volts peak to peak on the erase head. But that's channel 1. Channel 2, nada. And it's like, okay, well, something's going on. I know the oscillator's working because it's on track 1. The relay energizes, but there's still no signal on the record head, so I want to figure out why. And the best way to do that right now is to go ahead and use the scope for tracing out where the signal isn't. There it is. There is the 70 kilohertz. What I'm going to do now is actually, I'm going to go ahead and put this in record mode. So now it's in record mode. Record bias, 30 volts peak to peak for channel 1. Erase current for channel 1. And now to channel 2, there is 42 volts and 149.6. What happens is that I can crank it up, okay, and then I'm running it down, but what happens is it gets to a spot and then it just dies. It goes down to 4.8. I mean, it's like I'm just moving this ever so slightly and it's there and then it's gone if I go back a little bit. That's a problem. And I would like to be able to actually reduce it, but it's going to depend on what kind of recording tape we're using. And that's going to set up the amount of bias that's going onto the tape, because the record bias is actually setting up the tape to accept the audio signal that's going to be planted on the tape itself. And it's mixed in these two capacitors here, because the record audio is coming through this preamplifier here and the oscillator's over here. So the oscillator is mixing through this capacitor to the audio, and then it's going out the head to be landed, embedded, or imprinted. I like imprinted, that's good. Imprinted onto the tape, okay? But certain different kinds of tape, I mean, like I said before, in the good old days, you'd probably have 185 nanowebers, okay? Nanowebers is like the field strength of the bias that's going onto the tape. And tape formulations got better and better and better over time, and you could put more signal onto the tape, okay? It's what we called hotter tape, you know, so 185 to 200 to 250 nanowebers. Shoot, I think they're using 320 and 600 now, okay? Because the formulations have improved, and they've been able to figure out what particles to use on the tape in order to accept the audio signal, but you have to like be breathing fire onto that tape to just get it biased so that the signal will be there. But it's going to be a much hotter signal. The tape won't saturate, in other words. So that's why you wanted to have a higher nanoweber rated tape. This is from 1962, okay? They weren't thinking in those terms back then. They were glad to have tape they could actually produce that actually would play back something you recorded on it. So that said, this is where we're at. This pot is not working. And I have a hunch. I think when all of these capacitors were bad and excessive current was being drawn through this discolored resistor, I think that the excessive current was also being pulled through that pot. And I think it burned out that pot. And there's a good way to test that theory. What I first want to do is confirm that these pots are in fact 10K. So what I'm going to do is measure this pot. And I'm going to measure from end to end, not the wiper, just end to end. Okay? That should tell me what value the pot is. It's always a good idea to just like maybe put your voltmeter in here and find out where any of the voltages may remain. Capacitors get charged up, and once the cathodes and the heaters cool off, okay, the tube's not conducting anymore. So it tends to leave voltage in the capacitors, but it'll get your attention. All right, so let's see where we're at with this. Okay, and I can test this with it in the circuit because it's a rheostat. There's no lead on that far end. And this is measuring 10.6K. Just for grins and giggles, I could probably measure where the wiper is. Now, I don't want to measure it in the circuit. Okay, so what I want to do really is simply measure from the wiper to the unused end of the potentiometer and then subtract that from 10K and I'll know where the wiper is. 1K, which means that the wiper is at 9K. Okay, so the wiper is really at the far end with 9 kiloohms of resistance to the other lead. So now let's measure this pot. Okay, from end to end, nothing. It's an open, which means what's happening is it's not 10K ohms across this anymore. There is a break in it. And that also tells me that these pots are probably not carbon, okay? They are probably wire wound, okay? Another giveaway is the physical size of them. They're huge, okay? Now, granted, in 1962, everything was bigger back then. Don't chase that rabbit. Yeah. So anyway, they're big, okay? My guess is they're wire wound, and it's 10K ohms from end to end, but there's nothing there. Yeah, so there's a break between the wiper and the unused lug on this potentiometer. Gonna have to replace that. And I would love to know for sure that it's a wire wound, but just the physical size of that and the nature of the circuit that it's in, I'm guessing it's probably 2 watts minimum. So a 2 watt wire wound 10K pot, that's on the shopping list. And that's where we're gonna have to go next before we do much of anything with the record circuit that's in here. Now, let's just take a look at this thing. This is commonly referred to as a potentiometer, and in this particular case, it's being used as a rheostat, right? Because we're only going to be using 2 of the 3 leads that are on here now. The resistance is going to be used between this end of the stator and the wiper, okay? So it's only going to be basically a variable resistor as opposed to the wiper traveling between potentials, hence potentiometer. But let's take a look at this, because this is the one that's bad. And there. Okay, so we got the cap off. Let's take a look inside this thing. From these lugs on the ends, okay, here and here, on the inside of this thing, what we've got is a stator that runs from that lug all the way around to this lug. So the resistance in this particular pot is actually going to be 10 kiloohms. Okay, 10K. But the really interesting part about this, if I can get this in focus, you're going to see that this stator is actually wafer thin, and it has wire wrapped around it laterally all the way around. So if you were to take that wire off of that stator and stretch it out, it's going to be feet long. It's also typically of this vintage, it's going to be probably nichrome wire. And what ends up happening is that this top edge is bare so that this wiper can actually slide from end to end. These little tiny wires that are wrapped around that stator burned out. So we replace it. There's 2 more pots involved with this oscillator circuit. These 2 are for bias. These 2 are for controlling the oscillator. You have a pot right here that is for the oscillator itself. Now the oscillator, it's a dual triode, so when it goes to turn itself on through an RC time constant circuit in order to develop the frequency we're talking about, you're going to have a resistor and a capacitor that are going to create a time constant which creates a frequency. But because of the way the oscillator is designed, one triode goes positive part of the cycle, the other triode then conducts in the opposite direction. So you get a sine wave, okay, at 70 kilohertz. This pot right here actually controls the balance between the 2 triodes, because you don't want a real high peak here and then just a lesser one. So that pot is actually going to adjust the balance so that the sine wave is symmetrical. And that'll be important in order to create a lower distortion in the recording process. This pot right here acts as a dummy load for the oscillator when you're only recording 1 track. This deck is capable of stereo, but it's also capable of recording 1 track at a time. What happens is that when you change your track recording selection, okay, you can select 1 channel, we'll just say channel 1, stereo, channel 2. Well, stereo is going to be using all of that current to bias 2 record tracks on the head. It's also going to be loading up for the erase head to be erasing 2 tracks at a time. But when you go to 1 track, you don't want to feed all of that signal, bias, erase current to 1 track. So what it does is it will take what isn't going to channel 2, for example, and it actually will then send it to this dummy load through this switch. The switch will switch out that channel for recording and erase, and it basically loads it up onto this resistor here, which is just like a dummy load. And what this pot does here, it's going to simulate the load that isn't there because of the head switch for recording and erase. But it's burned out too. That's a 5K pot. So we're going to have to find a wire wound 5K 2-3 watt potentiometer in order to replace that one, because the same thing that burned this one out burned that one out. And that's a bummer, but it's not a deal breaker. And so we'll be replacing 2 pots, and we'll try not to get them confused. I think the thing I need to do right now is to just maximize my manpower. I'm waiting for parts to arrive in order to fix those pots that were in the RP unit. But I'm reminded of that question of how many does it take to screw in a light bulb? And so this episode is going to answer the question of how many minutes does it take me to screw in a light bulb? While we're waiting for the replacement pots to arrive, I thought we'd go ahead and tackle some of the cosmetic work. Now, admittedly, this is just totally covered in dust, but that's not really a problem, except that it's just not going to happen here in the laboratory because it's going to leave one hell of a mess. So that's going to happen outside of here, but in the meantime, I want to deal on some of the cosmetics, specifically these pilot lights that are here, which are basically attached and wired to this switch so that when you hit the record button, whatever mode you are in is going to illuminate a pilot light. Okay, so this is capable of recording stereo or one channel or the other channel, upper and lower. Well, as it turns out, Denon, in their infinite wisdom, they had basically come up with upper and lower. The upper and lower is simply because the way the heads are arranged in the head shell of the transport, there is an upper channel and a lower channel. Left is upper and first and front, and right channel is everything else. Problem is that the bulbs themselves are tiny. Also, as in the case of most bulbs now, back then, not nowadays, but well, there are some, but it's a threaded bulb, and it's really, really small, okay? Now, this bulb works, okay? And I've got some replacements, and this is going to be the replacement bulb, which is almost impossible to hang on to. But here's the rub. What you may find is that the lenses themselves are removable, okay? And you can often see the bulb that's inside there. And you'd be tempted, lead us not into temptation, but deliver us from light bulbs. You'll be tempted to try to take the bulb out. Well, at first glance, you see a bulb in there, and it's like, all right, well, then I'll just rig up something in order to be able to reach in there and unscrew that bulb. Typically, I would use a piece of heat shrink that I just basically heat a little bit of it so that it's flared at the end, but it gets a little bit smaller, okay? And then just reach in there and sort of grip the bulb with it, push it a little bit further, and then just start to unscrew it and try to pull it out of there. But here's the problem. Bulbs of this vintage, over time, the glue that they use to hold the glass envelope inside the base, okay, has deteriorated. The glass is actually loose in the base. So if you put a piece of heat shrink over the top of that and then try to unscrew the bulb, all you're going to do is twist the wires that are going to the glass envelope, and the base is going to be stuck inside. With this particular lamp fixture, there's another way to get about it. Investigate what your options are, okay? Because this could get ugly, all right? And when it comes to the cosmetic stuff, and I try to treat everything with the utmost care, all right? Because I'm lazy, all right? I don't want to make more work for myself. And if I break something, then I'm going to have to fix that, and then I have to figure out where I left off, and and I end up just ends up piling on. All right. So I want to investigate very carefully how to go about getting the bulbs out of there. Well, for one thing, when I first pulled the cap off, I didn't know the bulb was threaded, because there's no way to tell. So you really don't want to jump to conclusions, okay? Like I did, where I took a piece of heat shrink, put it in there, gripped the bulb, yep, got good grip and everything like that, started twisting it, and it felt like it came loose, and I pulled it out, and all I've got is the glass envelope of the bulb. The base is still stuck in there. So, live and learn. And that's why I'm sharing this with you, so that you can get your head around the possibilities that you end up making more work for yourself, right? And that's a bummer. What I have discovered also is that this base will actually unscrew from the mount. I'm going to unsolder these leads, green, black, or yellow, and this common wire, which is underneath here, okay? This common wire is attached with a white wire back here. So I'm going to unsolder those, and that way then I can just very gently unscrew each of these pilot light bases, okay? Then just screw the bulb into it, put it back in place, solder it, and that'll be done. So that one's cut. That one's cut. I'm going to take the excess wire from here out, but I'm going to leave enough on there that I can grip it, possibly pull it through later once I get to that point, but I don't want to snag anything with this tail hanging off that could possibly damage the lug. This now will actually spin. It's threaded. These are the solder points. And this is the threaded base inside there. So at this point is I'm going to try to thread that bulb in there. Now, this glass bulb is shorter than the old one. So getting a grip on there just to get it threaded in there is going to be a little bit of a challenge. But as I mentioned before, where the glue that they used to hold the base onto the bulb here has deteriorated over time, and putting a piece of heat shrink on top of that glass and twisting it out is going to damage that bulb. And what a shame. The bulbs probably were good to start with, and if I'd have known to be able to take this out, I would have been able to possibly get the bulbs out without damaging them and having to buy more. Okay, but what I want to do is just get a little piece of heat shrink. I want to be on the bulb enough to be able to thread it into the socket, but at the same time, I want to be able to pull it off the bulb without damaging the bulb when I'm done. Let's just test that theory right now. Okay, so that'll come off that bulb pretty well, and hopefully it grips enough to be able to thread it into place. And I believe we're there. There you have it. Bulb is in place. Heat shrink just basically fit over the bulb, allowed me to thread it into place, and we can check that real quick. Oh, look at that. I don't want to get it all back together and then find out the bulb doesn't work. I want to do this very gingerly because although I don't even really think this is Bakelite, I really think it's just really cheap plastic. It's not really very robust, and you've got these tiny threads on there that are threading into a steel part of this thing. There's that one. Okay, fully expect that to work later. Hope I'm not disappointed. You notice that there is no bulb in this one either, because somebody bearing a striking resemblance to myself broke it. We'll do what we can to sort of get it stretched onto the bulb just to provide enough grip for it to thread where it feels like it bottoms out. It feels like it has tightened up. Now, that nipple actually reaches inside there. Let's see. Oh, look at that. Okay, so I've got number 2 done. This one, because of its location, is going to be a little harder to thread into place. Just go real slow. If you feel it binding up at all, stop, back up, come at it again. Okay, because these threads, these plastic threads threading onto steel threads, they don't get along, and that's what's going to happen. All right. No bulb. You'd think after the first one broke I'd have learned my lesson, but nope. That looks as deep as the other ones. Yep. Now this one can go back in. And oddly enough, if you got it threaded back there the right way, these pins down here, these lugs are actually going to line up where they were to begin with. Now, as I mentioned before, go ahead and just cut those wires out of there, because I was going to replace it anyway. And that's going to be for this common bus that's going to run from this white wire and this lug over here to this lug, they all tied together. And then there'll be green, black, and yellow across the top. And I absolutely want to put my bulb threading tool back where I know to look for it. We'll get this bus all tied together. Got to measure. You know, I just sort of stuck it in here like that and measured, okay? It's like brain surgery with a chainsaw. You just do it by eye. Changed my mind. It's not going to be easy to cut, and I don't want to risk having that little snot of wire fall down inside here. So I'm just going to go ahead and go the extra mile and grip that and desolder this. All right, so one easy sort of cheat on this is I'm actually going to flow some solder back onto that. It's going to be still pretty warm. Grip that. Go ahead and then just reheat that, and the wire comes off. So now those little teeny pieces of wire that were left over on the lugs are off. There's no risk of them getting into the chassis and causing a problem thereof. I feel better about that. So I'm just going to go ahead and flow that onto there. Let's test the success of this before attaching the actual wires that are going to those pilot lamps. Just going to connect the bench supply to the common on all those three. Test each bulb in sequence. Well, that one's working. Okay. Stereo mode. And the upper channel, which is amber, white, and blue. Green, black, and yellow. Probably be a good idea to re-tin these wires. Put some fresh solder on there. So now, time to grab another cup of coffee, check the mail, see if those pots have arrived, and take this to the next level. And here we're going to actually take a look at the replacement of the pots that got burned out when all the capacitors leaked and drew excessive current and everything. So that's important. And if you go back to part 7, if you want to see the inside of one of those wire wound pots and what burned out, I get a chance to show that to you. So you can go back to part 7 for that. Part 9, we're going to actually replace the parts, but surprise, surprise, they don't fit. Well, here's what I did to take care of that. 1 coffee cup later and a pit stop thereof, ready to go after these pots. Turns out they arrived while I was on coffee break. Only needed 1 of each, so when you need 1, you buy 3. I couldn't get a 3-watt wire wound pot at 5K. It's just not available. But what I did was I got a 4700. So it's 4.7K versus 5, but at 3 watts. And that should be just fine. Yeah, he said should be. And then the 10Ks, which are 1 watt, a wire wound pot is going to handle more current than a carbon film type potentiometer rheostat would. The pot itself is going to go in this hole right here. This is bias for one channel. This is bias for the other channel. This one works, that one didn't, and it's about to. Those are the 4700s. That's going to go in place of this pot over here, because this pot turns out it's also bad. Why did the pots burn out in the first place? I mean, I just got done saying that, you use a wire wound so it'll handle more current, and yet clearly it didn't handle it too well. I want to get this in here. It's going to be too close quarters. The other pot's in the way. It won't quite fall into that hole because the diameter of this pot is larger in diameter than that pot. When I get over to here, it's not going to be a problem because there's a lot of space around there to deal with. The only way I can see to fix that is to open up this hole just a little bit so that I can slide this over enough to where it'll clear this other pot right here. I'm wondering if I can use a nibbler tool just to sort of notch this over in order to make enough room for that, and that the washer and the nut that's going to hold it in place will work. This, ladies and gentlemen, is the nibbler tool. One very important thing about this now is that as I nibble this, each piece of nibbled material, nibbled steel, you have to account for them. You don't want them just lost in the circuitry here somewhere that one day it's just going to short something out. So with each snap of the nibbler, I'm going to want to make sure that I have collected the scrap. And boy, I mean, just getting the nibbler in there, this pot's sort of in the way now. The only right thing to do is to take this pot out, get it out of my way, so I can get the nibbler in there and open this up. I want to be really careful because this pot is still good. Ordinarily, I would use a nut driver on that nut down there, but that looks like it's probably a 1/2 inch. First nibble. I just want to keep track of my scraps. There it is. I think the thing to do with this part is actually just come up here at a slight angle. So it didn't bite a lot, but it bit some. So you can see here that this pot now, this is probably the position where it was, but now I can move it over that far. It'll clear the space needed for this pot. I do want to get these two very close together because this little piece of wire right here actually was soldered between the two of these in order to take these cases to ground, sort of shielding, because there's a 70 kilohertz-ish signal at about 150 volts that's coming through these pots, so it wants to radiate. So they grounded these cases in order to prevent extraneous radiation of that RF signal. Yeah, it's only 70 kilohertz, but I still consider it RF. Because this pot is larger in diameter, it might tend to touch this barrier strip right here with a couple of layers of electrical tape, just in case it ever tries to like rub through there or something. Now we'll get the new pot into position, or a newly nibbled hole. Not only that, but I'm also counting on this washer to hide the multitude of sins that occurred in making that hole accommodate this new pot. I've desoldered the leads and the extra wire wound resistor off of there, the 5K. So we've got this out. I'm going to go ahead and just measure from end to end. Lo and behold, it's open. All right, so it's a wire wound pot. There's a break in the winding inside this pot somewhere. If I take and turn this shaft, at some point I'll probably, yeah, right there. So the wiper actually made connection with the part of the wire wound that actually does work. I can probably come back to this side I go from 1.2, maybe 1.6? No, 1.3 to open. And from this end, 1.5, that's it. So 1.3 ohms from this point to somewhere over here, and then from here to someplace right over here. All of this inside this pot here is gone. This new pot, although not 5K, is 4,700, so 4.7K. It's going to be pretty close, and it's going to do the job. I really have a good feeling about this. Now, you might be asking yourself, well, why is there even a dummy load in this unit? This unit is actually capable of recording one channel at a time, the left channel or the right channel, 1 or 2, all right? And as a result, if you switch from stereo mode, where you're erasing 2 tracks and biasing 2 tracks at a time, then when you switch to, in this case it says upper or lower, then you're only going to be recording one channel and erasing one channel, but there's still plenty of excess voltage there. So they put a dummy load in this circuit here, so when you switch from stereo and to one track only, it's going to switch in a dummy load to simulate the load that would be there if you were doing 2 tracks at a time. And that's what the dummy load is for. The pot that came out was 5K with a 5K fixed resistor across it in parallel, which means that at best, the most resistance you were going to get with those 2 in parallel was 2,500 ohms. You know, later on, there became more efficient ways of being able to do that, but this is ingenious. Now that I've got this basically upside down, you see the actual, business end of this particular chassis. Just to sort of touch base here real quick, this is the new bias pot that has been put inside. This is an original pot that tested okay, so it got to stay. Both of these are 10K, so those 2 are done. This is the new 4.7K pot, which is going to be for the dummy load. This pot here checks out fine. It is also a 5K pot, but this pot is actually important in this way. It's basically a balance adjustment between the signal going to the oscillator tube, because you got 2 triodes. So by adjusting that pot, you can actually adjust the gain so that the sine wave is symmetrical, and that's important. With the pot wide open and that 5K pot across there, I've got 2.46. All right, but now as I adjust this, and I'm going to get to where I think is about halfway, that's totally closed off. I have pretty good range on there. So the last thing to do is to go ahead and reattach this shield wire. And I think this new pot over here, this 4.7, is actually smaller in diameter than the pot it replaced, whereas this one was bigger than the one it replaced. This is smaller than it was replaced. That wire is going to be shorter to go the distance, so let's just do this. Let's just replace that wire. And so I don't want to risk heating this end of the wire up and having it simply melt the solder on the other end. All right, because that's going to be, it falls off there and it's going to be a pain in the butt. Here's what we do. Just put a hemostat on there, which will act as a heat sink so that the heat cannot get to that other solder joint. And we just flow some solder onto this. And that is a done deal. In this episode, we're going to take a look at the bias oscillator, now that it's repaired, which is also part of the erase oscillator, which is also repaired, because those pots got burned out due to leaky caps. Well, we're going to set this up on the scope. We're going to take a look at the amplitude of the bias oscillator. We're also going to look at the frequency, making sure that all of that's correct, because we can test it now that it operates, and this is how it looked. The next thing, get the scope fired up and check some of these erase voltages and bias settings. I just want to go back to the same places that I've been before. Now, one of these channels was not working because some of the pots were damaged. And so I want to go to a known good signal, which is on this Cinch Jones connector back here on pin 7. That's 155 volts, peak to peak. Boy, that is dead on, 75 kilohertz. One channel, 65 kilohertz. So I'm just curious now if the dummy load changes that frequency. No, changing the amplitude. I just want to try to get these all balanced. Now let's check the min stereo right there. That says 151.4 on that channel and 151.6. Beautiful thing. So let's see where we are on the bias. I don't know where the bias levels need to be because I don't have a particular piece of tape on here right now to set those biases, but there's absolutely no smoke. Now that we've got all of these components replaced and everything seems to be fine, we're going to go ahead and take some readings. And there we have it. That is the bias voltage on the record head. You're never going to really see the audio. The bias is a signal that is so strong that the audio is not going to be visible on the scope just yet. But I'm going to show you a way to be able to actually see that by going earlier into the circuit where with a capacitor they are coupling the bias and the audio signal together. That is the bias frequency, but on the audio side of a capacitor that's connecting the two. It's basically combining the bias with the audio. Channel 1 right now has a peak-to-peak value of 1.6 volts. So that is actually measuring 73.85 kilohertz. So I know that that is the bias frequency, but that is on the audio side of these capacitors. So let's just drop that back down again. Okay, get out of that. And let's apply some audio to this, just to make sure that we can actually see it. Okay, well, there's audio. What we're seeing on the scope right now is channel 1, which is in record mode. So the waveform is actually thicker because there is a 70 kilohertz sine wave that is on that audio waveform. And I know that's audio waveform because I can change the frequency of that audio waveform. So I know that that's the audio portion. I typically use 400 hertz. Okay, I think the book called for 700 hertz. Not sure why. If they picked 700, there had to have been a reason for it. Probably because that is the center of the frequency response curve for the electronics as designed. I'm using 400 hertz because I know what 400 hertz looks like, and it's going to be familiar territory. So there you have it. Now, just to be sure, I want to show you something here. I'm going to just increase my time base. Now, I'm at 1 millisecond right now. So, but as I increase this, you can see that the bias is there. Okay, it's not very large. Okay, as a matter of fact, let's just do this. Okay, I want to measure peak to peak from channel 1. Okay, and that is 5 volts, peak to peak. That's what I would expect to see. And obviously everything here is just behaving as it should be. I'm actually fairly pleased with that. I'm going to go ahead and stop the deck. That's going to just simply revert back to audio without the fuzzy parts attached to it. Now, I will point out that the record volumes on this RP unit are wide open. Okay, they expect you to do a test and calibration with the pots wide open. I get that, because that means that there is actually no additional resistance in the audio path through the circuit in order to make sure that the levels are supposed to be balanced. I do want to point out a couple of things. With the record volumes all the way open, okay, and tone present, but I'm going to go ahead and switch these switches to the record monitor so that we can actually see the levels going into the deck. All right, so that's not exactly 0 dB. There is a calibration on the RP unit, and those calibration adjustments are right here. That's one channel, and that's the other channel. And what those are going to do is actually adjust the record level going through the electronics to be combined with bias on its way out. I always like to go low at first and then gradually bring the meter up rather than going past 0 and bringing it down. There's no right or wrong way of doing it. The manufacturer has already determined what value of resistor is needed for the meter to register 0 dB with the proper record level going to the head. You can get to those resistors and change them out, but the procedure is, in order to get it correct, you have to record on the deck first, get the levels set properly so that the deck is performing to specifications, and then you change those resistors in order to make the meters read 0. All things being equal, this is the way that it would have to be calibrated in order to set up the record. But what I'd like to do right now is just go ahead and button this up. If I need to make any other kind of electronic adjustments, I'll be able to get to them with the pots on the top of the chassis. So I really don't need to be in here anymore. It's been running for a number of hours, and at no time have I let the smoke out of any of the components that are in here. So I'm happy. The fire department is happy. They didn't have to be called, and everything is cool. So let's get this buttoned up and put a tape on there and see what it sounds like. I think that I'm going to be ready to button this all up, okay, and put it in a nice cabinet and clean it all up and everything like that. Surprise! While we're here, I wanted to show you something that I thought was really impressive. You can cue the tape that tight and this thing just instant start. And for 1962, that's pretty impressive.
Desert the skies, fantastic in your arms. When we walk hand in hand.
So I'm confused. I've been trying to trace audio through this chassis, you know, just going through the throughput, and you might have even noticed a moment ago that it just kind of confounded me, and I couldn't account for it, okay? Because through an audio chassis, inputs to outputs, left is left is left is left, right is right is right is right, and this is just not behaving that way, and it's like, WTF? I mean, come on. So anyway, we're going to look at this, all right, because I think I know where the problem is, but these things can happen. And of course, the first inclination is to blame yourself. It's like, well, what did I screw up? Okay. But the first rule of engineering, okay, if something was working, operative verb being was, if something was working and it isn't anymore, you ask yourself one question: what's changed? So something changed. Of course, in this particular case, the change may have been at birth, okay? And I won't even go into all of the analogies about being swapped at birth, but this may qualify. I want you to see this. This is the actual cover of this chassis, okay? And I got another cover for another chassis right back there. It's identical. It's labeled the same way. You take my word for it. As a point of reference, the AC power is right here. Well, AC power is right here, which means that this would be output 2. And then the next one would be output 1. Right down here at the bottom, the inputs are 2, 1. So 1 would be on the very, very bottom, right against the edge, okay? So that's a pretty reliable map. I've got my scope probes here, and I'm gonna put the probe on channel 1, right down there, channel 2 on channel 2. There's a technical term for that, duh. Now, we'll take a look at the scope. I'm gonna play tone. Sorry, producer. In fact, you want to skip past this part, I wouldn't be surprised, all right? But this is what kind of really pissed me off, all right? Because now that I've established channel 1 left all the way to at least the meters, now let's look at the output. Right channel, left channel up there. Left channel, right channel up there. The channels at the output are swapped because the input's good, the pot is correct, the meter is correct, but the output is swapped. Is it really? Well, let's take a look at that. All right, I'm thinking, all right, well, maybe it's something obvious, otherwise I'm gonna have to do a signal trace through each of the stages through this amplifier to figure out where the swap has occurred. And I mean, I just got done recapping this thing. I mean, if something had actually been miswired, I mean, it would have popped out at me. It would have made itself known. But I did notice something rather interesting, okay? And I'm going to use my Mega 6R officially pointing tool, okay? Well, let me clean the soy sauce off this. I noticed that the cable for the channel 1 channel here is gray. Right there, channel 1 is gray, and the channel 2 wire is black. Now, it doesn't mean that if it's the wrong color, the electrons are gonna go the wrong way. That's not what it means, but it means that somebody had the attention to detail to actually use different colors between channels, okay? I mean, they used red and white, okay? But you know, a long, long time ago, things weren't in color, so they had gray and black. Something I noticed that kind of jumped out at me. Gray is on 2, black is on 1. But down here, black is on 2, gray is on 1. These are swapped. And you know what? Here's the thing that really gets me. It really doesn't look like it was an aftermarket modification. It looks like it came from the factory that way. I mean, dollars to donuts, that's original solder. So it's like, I mean, these cables seem to be pulled to length. I mean, they were cut. This black wire here is actually probably going to be shorter than the gray one. Going to lay this down, fire up the solder iron, wet my sponge, and get a cup of coffee, and we're going to go ahead and make the change on this. So let's see what other trouble we can get ourselves into. You know, we're going to cut them and swap them. There's just too much potential for damage in the close proximity of this. So the gray is going to go below, and the black is going to go above. The gray wire cable jacket is attached to 2, but these center conductors up here have been swapped between channels. And that is going to solve the mystery of channel reversal. Rule number 17, okay? If you're smart, you can do it without being smart. This has been fun. And I'm gonna go ahead and get this all flipped back over and everything like that, run another smoke test on it, make sure everything's cool. And just, you know, sit down, decompress, and enjoy it. Repairs, restoration. We've only got that much left to do, okay? It's fully operational, but now we get to do the alignment and calibration. And I'm gonna have a special treat for you. At least I hope I'm not lying, okay? But I've designed a cabinet for this thing. Now, these were never intended to be in cabinets. They were supposed to, you know, back in those days, everybody installed stuff, Okay, and everybody, you know, you had a blender in your kitchen. It was built into the countertop. I mean, people had hi-fi systems, and they had, you know, a knockout or something where you could actually put a tape deck in there, or a record changer on top or inside. You could basically building it yourself. It was all built in. Well, this is not going to get built in. I designed a cabinet for it. We're going to have somebody build it up for us, and we're going to bring that to you as soon as it's available. If you like what you've seen thus far, I know I do, give us a thumbs up. Subscribe to the channel because it helps let you know when episodes are dropping, and your comments, just keep them coming, and we'll keep them going. All right? Patreon subscribers, thank you so much for helping us out. It gives you access to uploaded documents. It gives you access to detailed, unedited, in a matter of speaking, episodes, okay? And merchandise, okay? Patreon subscribers get a hold of that, all right? In the meantime, thank you for watching, and we'll see you in the next one.